If you've been following the work at Republic Analytics, you would have seen that the team here have been developing technologies to synthesize health data for the last little while. We've spoken a lot about the synthesis of clinical trial data. And in today's presentation, we will discuss the synthesis of real-world data and also talk about the simulation of real-world data. The main theme for my presentation will be the synthesis and simulation of COVID-19 data sets. But of course, the basic principles apply to any other kind of real-world data. We'll use a simple COVID-19 data set to demonstrate the methods and results and show the potential for using simulators to enhance and augment real-world data. We're very excited about the possibilities from these simulators, and we will discuss them, some of these opportunities during the presentation. Also note that the technology that Republic Analytics has developed supports the creation of these simulators and their application in different situations. So let's start by providing a definition for real-world data. An easy definition, of course, is what it is not. Real-world data is not clinical trial data. It is data that is collected from routine patient care, for example, data from hospitals, pharmacies, payers, and from labs. The data can also be collected prospectively, as in some disease registries and observational studies. Or the data can be patient-generated from, for example, social media, wearables, mobile devices, and sensors. Data from surveys and patient support programs can also be considered as real-world data. In our specific context, which is the COVID-19 context, we're using case data, which would also be considered real-world data. Patient-reported data related to their experiences and exposures would be classified as real-world data. This slide just shows some examples of the general types of use cases where real-world data has been used. This context, I think, is important because it illustrates how data synthesis and data simulation can be used and can enable some of these use cases. So I'll highlight some of the items here that demonstrate the value of real-world data. So you're using real-world data as an external control arm for clinical trials is a very interesting use case. It means that instead of having a randomly assigned control group in a trial, real-world data is used instead. Patients from real-world data databases are matched with patients in the control arm. These real-world data patients play the role of patients who receive the standard of care, and the matching process ensures that the control patients have similar baseline characteristics as the treatment arm patients. Of course, you also need to have comparable outcome variables for the control arm as for the treatment arm. So in some cases, this is easily achievable. For example, if the outcome is survival, then that's a very objective measure that you can use. So as you can imagine, using real-world data in such a manner can result in significant cost savings for running clinical trials. And as importantly, it also means that trials can be started much faster and can be completed much faster as well, because you need to recruit significantly fewer patients. You essentially recruit patients for your treatment arm and match against real-world data for your control arm. In the context of COVID-19, the control arm patients are those receiving the standard of care, and they can be matched against patients receiving a specific treatment. And of course, the availability of such real-world data can accelerate COVID-19 trials. Another high-impact application of real-world data is identifying patients that are eligible to participate in a trial. This allows trial sponsors to select sites for their studies, but access to real-world data for this initial screening of sites is critical for planning and budgeting. So the CROs and sponsors that are designing clinical trials need to access real-world data for each potential site to make these determinations. If a site does not have enough patients with a particular disease or particular conditions, or they meet some of the exclusion criteria, then that site would not be considered for the trial. So access to real-world data for recruitment and site identification can also be a key role for having much more efficient clinical trials. So these are just examples of high impact applications of real-world data. So let's talk about data synthesis and where that fits in with this picture. Basically, there are a few problems with the promising picture that I have been presenting to you. The first problem is that due to increasingly strict data privacy regulations and the growing strictness in interpretation of these statutes by regulators and courts, it is becoming more difficult to get access to real-world data. Or the data that is being shared has been transformed so much that the ability to get meaningful analysis out of it has been significantly diminished. This is not a new issue, but it's getting more acute, and the COVID-19 pandemic has created a real sense of urgency to solve this problem. Access to real-world data is going to be critical to understand the disease and to respond to it. This access has to be with limited restrictions. Providing access to data with many restrictions and controls in place limits the number and heterogeneity of data users. So data synthesis can provide a solution to this data access challenge because it solves the privacy problem. The next big challenge is small data. We see small data when we are dealing with rare diseases or when the population under analysis is small. The problem with small data is that it is difficult to use some of the more sophisticated machine learning techniques on them. Many advanced analytical methods require large data sets to work well. If you have a small data set, it limits your ability to use some of these techniques. Small data also occurs when data collection is expensive and when data collection is slow. Therefore, it's not economical to collect large samples, or the time it would take to gather sufficient data would mean that analysis results would not come in time to inform actual decisions. In those situations, data synthesis can play an important role by using the generative models from data synthesis as simulators. This is where simulators comes in. Another scenario, or a third scenario that's interesting, is relevant when data is collected, but we want to perform an interim analysis by simulating the whole study. So again, using generative models for these kinds of simulations can solve the problem of doing an interim analysis when only partial data has been collected. And finally, a variation of the last example, simulators can allow us to design smaller studies to start off with. So even if the data set that is going to be collected is not small, you can design a smaller study and then use the data from the smaller study to simulate the larger study. The cost savings can be significant, but more importantly, the speed of getting insights and the time to actionable information can be dramatically improved. So we'll see how all of this, all these issues can be addressed using simulators and the generative models that we create when we are synthesizing data sets. So let me talk a little bit about the synthesis process and then kind of walk through an example of synthesizing a COVID-19 data set and then building a simulator from it. The basic idea behind data synthesis here is that we take a real data set to start off with, and we build a generative model, which is the fit model in this picture, from that real data. This generative model or synthesizer model captures the patterns and characteristics of the original data. We then use this generative model to synthesize new data. You've probably seen deepfakes before. These are the images at the bottom right-hand side of the slide. So these pictures are not of real people. These images were produced using a generative model that was trained on large data sets of real people images. The idea is very similar when we are generating synthetic structured data. So we take real structured data, we build a generative model by fitting it to that real data, and then we use that generative model to create synthetic data or fake data. So the synthetic data is produced from the model. There are a few things to note about data synthesis. The first is that the process is stochastic. This means that every time we generate a data set, we will get a slightly different variant. This still maintains, or each variant still maintains, the patterns and characteristics in the original data set. The second thing to note here is that we do not have to generate the same number of records as the original data. So if we build a generative model from 1,000 patients, so if the source data has 1,000 patients, we can create a data set with 5,000 patients or 7,000 patients. while still maintaining the patterns and characteristics in the original data. So this is where the idea of the simulator comes in. When we build data simulators, we're using the generative model as a simulator. We are providing some initial values to the simulator, which consists of our generative model that I showed you before, and then we're using it to generate new synthetic patients. We can generate few or many patients. For our presentation, we'll just assume a simple simulator for now. We'll assume the same initial values as the real data, and we'll augment or create more patients from the generative model, rather than trying to manipulate the input values. If you follow us and attend some of our subsequent presentations and webinars, we'll discuss how you can do some more sophisticated simulations. But for now, the idea is we use the generative model, we use the same initial values to create more patients with similar characteristics as the original data set that was used to create the generative model. So now let's look at our example here, the data set we will use to demonstrate some of these concepts, the Canadian COVID-19 database. This is the case database provided by the Public Health Agency of Canada, and we obtained it through Esri Canada. The database, at the time when we obtained it, had approximately 100,000 records in it, covering the whole country. This slide shows the variables that, in the data set that we examined. So there's a date reported, which we converted to a number of days since January 1st. There's the health region, there's the age group. The data was collected as decades, gender, and then exposure. You have different categories there. The case status, so whether the patient recovered, is deceased, or the case is still active, and then the province. For a lot of this, for a lot of the data set, for many provinces, there were not reported values for a number of the variables that are important for our analysis. So actually, we performed our analysis only on Ontario, and there's just over 32,000 cases covering Ontario. So the first step in our analysis then was to create a synthetic version of this data set. So we ran this data set, the 32,000 Ontario cases, through the replicate synthesis software, and we generated the same number of records as the original data set. So we essentially have a synthetic variant now of the Canadian COVID-19 case database. So that's simple enough. So let's look at some of the characteristics of this synthetic data set. I'll just show you a few metrics comparing the real data set to the synthetic data set. So one obvious way to compare the data sets is by looking at the distributions of the individual variables, the marginal distributions between the real and synthetic data. So in these charts, we're looking at age or age group, and the blue is the real data set, and the orange is the synthetic data set. As we can see, the distributions are very similar between the real and synthetic data. They're not exactly the same. We don't want them to be exactly the same, but they're quite similar in terms of distribution. And then we'll look at a few more examples. This is the case status. So as you can see, across the whole data set, a good chunk were not reported, but for Ontario, the data set was complete. So we have active, deceased, and recovered as the main categories for which we have valid data. And then you have different types of exposure. Again, the differences between real and synthetic data sets are small. The synthetic data follows quite closely the distributions in the real data set. And finally, gender. Again, this is across the whole 100,000 records. For Ontario, we have a more complete subset. I have here similar distributions between real and synthetic variants of the data set. So we created a synthetic data set that looks quite similar from a univariate perspective to the real data. Now, another important metric that we use to evaluate the quality of the synthetic data is distinguishability. And distinguishability is a data utility metric that computes how well a discriminator can tell the difference between real and synthetic data. This is actually a tough test to pass, because discriminators are very powerful at detecting small differences between the real and synthetic data sets. In our case, we use a gradient boosting machine. We score this ability on a scale from 0 to 1. So a value of 0 means that the discriminator is not able to tell the difference between the real data and the synthetic data set. It means that the synthetic data set is very similar to the real data set. A value of 1 means that the discriminator is perfectly able to tell the difference between the real and the synthetic data set. So we don't want our synthetic data to be at either end of the spectrum, at any of these two extremes, because the former suggests the generative model may have overfitted and essentially replicated the original data, and the latter case would mean that the synthesized data is very different from the original data set. So the synthetic data basically is not a good reflection of the real data. So as a general heuristic, we like to see the distinguishability score in the lower quintile, so 0.2 or less. Just from our experience and observations, when it's 0.2 or less, the data utility tends to be quite high. And like I said, distinguishability is quite a high standard, quite a high bar to meet, just because the discriminators are very powerful at finding small differences. So in this particular case, we see that the synthetic COVID-19 data set meets that threshold with a distinguishability value that's quite a bit lower than 0.2, which basically makes the point that overall, in a multivariate sense, the synthetic data set has a high utility. Okay, so we created the data set. Now let's look at what we can do with it. So we built next thing, we built a logistic regression model that is predicting death as an outcome. And this is for the 32,000 odd cases in Ontario only. And the model had, as I mentioned, death as an outcome, and then 3 variables as predictors. We have age, gender, and the date reported. And the numbers shown here are the odds ratios. So there's a significant relationship between age and death, quite a strong relationship between gender and death, with higher odds ratios for males. And then a negative relationship between date reported, so death rate is decreasing over time. And here you can see the values, the odds ratios for this model between the real and synthetic data sets. The asterisk means that the value was statistically significant at the 0.05 alpha level. So as you can see, that the actual odds ratios values are very similar to each other between the real and synthetic data sets. The conclusions are the same from the perspective of statistical significance, and directionally also they're the same. Again, we don't expect the odds ratios or the values to be exactly the same, because it's not exactly the same data set, but really the objective is to be able to draw the same conclusions as you would from the original data. And in this particular case, we would draw exactly the same conclusions from the synthetic data as the real data. So, so that's the next thing, is we built a model to characterize death from the synthetic data that's quite similar to the real data. So now let's look at some simulators. So there's a lot happening on this graph. So let me explain to you what we're looking at here. So right now what we did was we took some samples from the Ontario data, and the bottom x-axis here, you can look at the sampling fraction. You have 5%, 10%, 15%, etc. So we created small data, and we then used the same synthesizer to create a generative model from the small data, and then use the generative model to simulate all 32,000 cases in Ontario. And then from this simulated data set, we built the same logistic regression model that I showed you. So we're essentially mimicking the situation where I only have a small data set. I only have 5% of the full data set, I only have 10% of the full data set, et cetera, all the way up to 95% of the full data set. And I'm using the small data set to create a generative model, and then I'm using generative model to synthesize or simulate all 32,000 cases. And the straight line across, the horizontal line at 3 is showing the odds ratios in the real data, and the dashed line below it at 2.9 is showing the odds ratio from the full synthetic data that we saw before. So as you can see that at around a subsample of 20–25% or so, we are getting quite close to the real value. So at that point, we're about 2.85 with the odds ratio, and it can then kind of hovers, it plateaus at that point, basically. So what we're seeing here is if we had a small data set, about a quarter of the size of the full data set. So if we didn't have, or were not able to collect the full data set, we only had 25% of the data set, and we use that to simulate the full data set, we would be able to build more or less the same logistic regression model as if we had the full data set. We see that pattern again here for gender. The same thing, the straight line is the real data odds ratio, the dashed line is the full synthetic data odds ratio, and then what we're showing here is the different sampling fractions. The value for the odds ratio when we create a generative model from a subsample. By the way, I didn't mention this, of course, the lines are the medians and 95% confidence intervals. When we simulate this, we repeat this process 1,000 times. So this is, we essentially did a simulation of the simulator that if we generated, let's say take the 5% sample, if we took a 5% sample 1,000 times and created a generative model, and then used the generative model to create the full data set, and then built a logistic regression model from that. So essentially, we're simulating the behavior over 1,000 iterations. So for gender, again, we see around 25% subsample. You see the median here is getting quite close, starts to plateau. In terms of the odds ratio for logistic regression model, starting to stabilize, and it's still quite close to the value that you would obtain from the real data set. And then for our third variable, the date reported, we see the same patterns around 25% or so. The odds ratio, again, is starting to plateau, and it's quite close to the original value. Again, it'll never be the same, but with only 25% of the observations, we're able to create a full data set or simulate a full data set and obtain more or less the same results. The last graph I'll show you on this, this is a decision accuracy for the three variables in our model, and the decision is whether the odds ratios are statistically significant. So as we can see, around 25% or so, we're starting to hit the 95% accuracy. So again, if we have a subsample of around 25%, and we use that to simulate the full data set, we would be making the correct decision regarding the statistical significance of each one of the variables around 95% of the time. So what all of this demonstrates then is that if you're able to build a simulator, which is essentially a generative model, and use that to augment your data set by essentially multiplying it, then you can address the small data problem. So the two scenarios we demonstrated are you can create a synthetic variant of the data set and then use that to do your analysis, which solves the privacy problem. And then we demonstrated the small sample problem. as well, where you can take a small sample and simulate the full data set, and you get more or less the same results as if you had the full data set. And the threshold we're seeing is around 25% subsample allows us to achieve this. And if you follow us and attend some of our subsequent webinars, then we have a couple of papers coming out on this topic as well. So you'll start seeing more information, more details about this analysis. Now, of course, this was a relatively simple data set in that we built a small model. And things get really interesting when you start working with more complex data. But really, the plan for today was to demonstrate the basic concepts and show how this could work, and to illustrate the concept of simulators and how you can augment small data sets to create larger studies, basically, or simulate larger studies, and then with these simulated data sets reach the same conclusions. And of course, more analysis has to be done to increase the weight of evidence and so on, but this just illustrates the potential here for what you can do with this type of data. So I will, and then of course, as I mentioned, we'll be sharing more information, more details about this approach and case studies and examples from other products and other data sets over time. So hopefully you'll be able to join us in subsequent presentations to hear more about this. So that is my presentation around the simulation of COVID-19 data.